So this is measurement of an object's characteristics from a distance, using reflected or emitted electromagnetic energy. Well, actually, it's not just electromagnetic energy. We also use sound, but the very vast majority of remote sensed imagery is generated using electromagnetic radiation. In a shorter definition, remote sensing is collecting data without directly measuring the object. So the simplest device are our eyes. Obviously, our eyes do not measure objects directly, unlike our hands, where even without some measurement tape, we can use our hands to roughly measure the size of certain objects. Why do we use remote sensing? Well, it's used in a variety of disciplines. I already talked about disciplines that use aerial photography. The same applies to remote sensed imagery. But there are a variety of reasons why we do that. It really gives us a comprehensive view of the Earth's surface. So it's much more than measurement on the surface, where you have limited access to certain sites, where it's really hard to collect data. It also gives us a comprehensive view. It's an accurate collection of spatial or geographic information, in a sense that there are certain features that cannot be found by just looking at the surface from the position of a human standing on that surface. The archaeological sites being a very, very classic example of it. And the third thing, so it's systematic collection of geographic data, it's accurate collection of geographic data, and also it's temporal, and the frequency also gives us the ability to observe change over time. And that's very useful because Earth is not a static object, it's very dynamic, complex system. And therefore, getting changes over time allows us to identify processes which also help us to manage the environment. We do it with certain level of success, but that's a completely separate topic. Okay, and I have really just a few examples before I move on to the process. So here is an example of just one image. Well, you can easily visualize it as a collection of images showing a Mississippi River sediment plume. That's the portion where you have delta, which is kind of like the end of the river, where the river gets to a bigger body of water, a lake and a sea, an ocean. And you can see in this particular image that Mississippi has to carry a lot of sediment, which then which then accumulates in the shallow waters that are close to the coastline. Now, there are practical, so that's sort of maybe more for scientists who are interested in environmental change, but obviously there's tons of different applications that are for businesses, agriculture, which, for example, in this case, allow us to identify healthy versus stressed vegetation, grape vines. You have two images here. One is the combination that kind of gives us a real the photo that you would see more or less from above. But then you have also infrared image, which is that portion of the spectrum that is outside of visible light. So we can't see that with our own eyes, but doesn't mean that it's not there. And infrared imagery is very, very useful for vegetation analysis. That's because it's something I'm going to talk about a little more later, but the major reason why infrared radiation is useful for vegetation is that the most, let's say, brightness, it really has a different name, but let's talk about brightness at this point. The most brightness that you can get from vegetation when it's healthy is in infrared. And if our eyes could depict infrared radiation, if you looked at green, healthy vegetation that is in its peak during a year, you would be blinded. It's so intense. And that basically allows us to identify, like, you can see certain areas where you have really healthy vegetation because of the very, very bright red color. That's a false color composite image, meaning that it's not really, because we can't see this portion of light, it's a false color composite. We are just adding certain colors to kind of get for us to visualize it better. But what you can get from this particular image is that certain areas it's more clear to identify certain areas which are more stressed. These are the areas that are less red. Why do you use that? Well, there is something called precision agriculture, where instead of, for example, using irrigation over the entire area, if you are a farmer who has really, really large, more of an industrial farm, obviously it's financially or monetary inefficient to irrigate the whole plots, right? It's better to target areas which are under stress, for example, due to dry soil. And in this case, you can identify those areas, and you can then like target those areas for irrigation. Okay, let's now talk about the type of sensors. First of all, the device that collects and creates remote imagery, remote satellite imagery, these devices are called sensors because they sense energy that is reflected. There are two types of sensors. Those that are mostly used are called passive, meaning that they only detect natural radiation reflected or emitting by an object. So in this case, you don't really, that device is just records data. It doesn't send anything, okay? And passive is really the vast majority of sensors, like our eyes. They do not emit any energy, right? That would be really creepy if our eyes were emitting energy, and they would be like bright red or even like light bulbs, for example. So they are just passive. Satellite sensors, cameras, video recorders, all these are passive. Then we have sensors that are active. Those sensors emit their own source of energy, which then gets to the object, bounces back, and it's registered back by the sensor. And why do we use active? Active sensors are much more expensive, which you probably could guess, because producing or emitting their own source of energy adds cost to the whole data collection. But they have certain advantages. They can be designed to minimize any type of weather or atmosphere irregularities that actually affect the quality of the photograph. They work day and night. All right. You don't really have to have sunlight to collect data. You can do it at night. It doesn't really matter. And they are usually, because of the fact that they are targeted, and what you select specific type of radiation or waves, they provide much higher quality imagery, but they are expensive, so we don't really use them that much. So what are these? Were the ones that you are probably familiar with, or at least heard about, are radars that use radio waves, focused light, which is the laser beam, and these are called LiDAR, and then sound, which are called sonar. Sonars, right, that kind of first thing we think about, the submarines. Radio waves, probably similarly. I don't really know this. I'm not really a military person and definitely not an engineer, but I guess when you can't really see anything, the radio waves give you some sort of information about what's happening. And then laser beams are more recent. LiDAR, very expensive, but really very, very accurate. All right. So the process. There's obviously some sort of a process behind how we register that and create those images, or what's happening, how does it occur? Well, here is a very simple diagram that actually illustrates the whole process very well. I really apologize for that. Oh, there you go. Let me go back to the slide. Okay. So first, we have the source of energy. As I said, most of the sensors are passive, so that's going to be sun. If you have an active sensor, that could be a sensor that emits a laser beam. It doesn't really matter. You have some source of energy that is going to illuminate a surface. Unfortunately, because there is a certain medium between the source of energy and the surface called the atmosphere, not everything gets to the surface. Certain portions are being bounced back within the atmosphere. Certain portions are absorbed, which is good. For example, UV radiation, that's good for our bodies when it's absorbed. So only certain portions of the energy that's being emitted actually gets to the surface. That energy, the total of the energy that is emitted from the source and that illuminates the target, is called incident energy. That's just the name for this energy. Now, this incoming electromagnetic radiation is then reflected. And that reflected energy goes through the atmosphere again. So we have another obstacle, the atmosphere, again, before we actually can register that energy using the sensor. Now, the easiest example of the obstacles in the atmosphere would be clouds, right? Oftentimes when you get satellite imagery, there's very high cloud cover and you can't see the surface at all. But that's why we use portions of electromagnetic radiation that are outside of the visible light, because certain portions actually don't see clouds as an obstacle. They go through clouds without any interaction whatsoever. So anyway, when that incident energy is being reflected, goes through the atmosphere, and whatever gets through the atmosphere is then finally recorded as the bunch or set of digits, and that comprise the image. Now, there is also one other energy that can be recorded by the image that is not really reflected, at least not immediately, and that's emitted energy. The emitted energy is really kind of reflected in a sense that this is part of incident energy that was absorbed and then emitted later on. All right, so it's really part of incident energy. It's not just directly reflected, but first absorbed and then emitted. And the one that comes to mind immediately is heat. So you've all seen images where you have heat shown on an image. That's actually emitted energy, not reflected energy. But let's just talk about the reflected energy, which just gets to the surface and then um, is reflected or bounces back as a beam and gets to the sensor. So how do we get an image? Well, different portions of radiation are going to reflect different different types of energy within the whole electromagnetic spectrum. And that is what gives us the detailed image. So grass is going to reflect a certain percentage of incident energy. Bare soil is going to reflect different percentage of the incident energy. And when you look at that, that's being registered, and you look at that, and then you have the variability of the reflected energy that collectively is the image. Here is a more detailed diagram showing incident radiation. So again, the incident comes from sun, and then it's split actually into three types of energy. First is the reflected one. That's the one that we actually are interested in, because that's what gets eventually to the sensor. Then we have a certain portion of incident energy that's being transmitted. A good example of that is tree canopy. If you stand under tree canopy in summer during very, very good sunlit day, you can see like there is a sort of like an aura, maybe green aura, where the trees are to some extent translucent, right? Because you can see through them. That's the transmitted energy. The energy is not reflected from the leaves directly to the sensor, but gets to the surface through the leaves. So that energy is being transmitted to the surface itself, because tree canopy is not on the surface, it's above the surface. And then we have portion that's being absorbed, and usually later on in some portion radiated back in the form of heat. So whatever the total that strikes is really a sum of the reflectance, the absorptions, and the transmittance, or reflected energy plus absorbed energy plus the transmitted energy. And I like to call it IRAT. That's just easy to remember. This particular function equation. But what we are really interested in is the reflected energy, because this is the energy that we can ultimately record via our sensor. And the most important, probably, equation in remote sensing is spectral reflectance. And spectral reflectance is a fraction or a proportion, usually multiplied by 100 to give you a percentage. That's kind of standard, but it's a fraction nevertheless. So that's the portion of or percentage of reflected energy divided by the total incident energy and multiplied by 100. So there are certain, so what does it mean in practical terms? Well, as I said, if you have different surfaces, the incident energy, roughly speaking, is equal. Whatever gets to the surface eventually is the same amount. Well, as I said, roughly, because we have different obstacles for over different areas, and that sort of added complexity to it. But let's assume that roughly the incident energy is the same. Now, the percentage that's being, where are you, my pointer? The percentage that's being, I hate these pointers, I can't see them at all. The percentage that's being reflected varies by surface. So the reflectance is going to be different for different surfaces. And it's actually a measure. It's a real number. It's nothing fancy. It's just mathematics or physics, actually, to be exact. So again, you have to remember the most important remote sensing theory equation is spectral reflectance. Everything relies on spectral reflectance. And that's the percent of total incident energy that's reflected from an object.